Hello, and welcome to this lesson on the sizes of particles and their properties. In today's lesson, we will compare nanodimensions to the typical dimensions of atoms and molecules. We'll then understand the relationship between the surface area to volume ratio and size reduction in nanoscale structures. In the previous lesson, we have understood the use of nanometers for measurement and briefly delved into the properties of nanoparticles. We will build on this foundation today and deepen our understanding of those fascinating particles. Atoms and molecules are incredibly small. To give you a sense of their size, atoms typically measure between 0.1 and 0.5 nanometers in diameter. Molecules, depending on their complexity, may be slightly larger, but are still within the range of nanometers, 0.1 to 1 nanometer. Nanostructures, such as nanoparticles and nanotubes, are larger than individual atoms, but still extremely small. They range from 1 to 100 nanometers. One example, which we've come across previously, is a carbon nanotube. The scale of those nanostructures is largely responsible for their unique properties. One of the most important features of nanostructures is the relationship between the surface area to volume ratio and the size of the particles. To understand this, let's consider a simple geometric shape, a cube, each with a side of 1 centimeter. The surface area of a cube is determined by summing the area of the faces. There are 6 faces, and each has an area of 1, giving a total surface area of 6 centimeters squared. The volume of the cube is given by 1 cubed, so 1 centimeter cubed. Therefore, this has a surface area to volume ratio of 6 to 1. Now suppose we bring 8 of those 1 by 1 by 1 cubes to form a larger 2 by 2 by 2 cube. As this larger cube is made up of 8 smaller cubes, it will have a volume of 8 centimeters cubed. You might be tempted to say that the larger cube's surface area is 8 times the smaller cube, but notice that for each of the small cubes making up our larger cube, only 3 of their faces are exposed. This gives a surface area of 3 centimeters squared. Exposed per cube multiplied by 8 cubes equals 24 centimeters squared. Hence, we have a surface area to volume ratio of 24 to 8 or 3 to 1. This is significantly smaller than the 6 to 1 we obtained for the smaller cube. This shows clearly that changing the side length has differing effects on the surface area and volume. In fact, if you were to reduce the length of each side of the cube by a factor of 10, the surface area decreases by a factor of 100, while the volume decreases by a factor of 1000. This means that as the size of the cube decreases, the surface area to volume ratio increases dramatically. Relating back to the nanoscale, this means that nanostructures have very large surface area to volume ratios, giving them unique properties. This increased surface area to volume ratio has significant implications for the properties of materials at the nanoscale. High surface area allows for greater interaction with the surrounding environment. This means that smaller quantities of nanoparticles are needed than the corresponding bulk particles. The increased surface area also means they make nanoscale components stronger and more durable. It also has impacts for their applications. For example, nanoparticles are excellent catalysts, speeding up chemical reactions very effectively. This is due to their large surface area ensuring there are more sites for reactions to occur. Furthermore, nanoparticles are used in drug delivery to transport and release medications within the body, and they are able to do this efficiently as the higher surface areas means more drug particles can interact with cells or tissues. In summary, comparing nanodimensions to atomic scales helps us understand just how small nanostructures are. Understanding the relationship between surface area and volume as we reduce the size of particles underscores why nanomaterials have unique and beneficial properties, particularly due to their large surface area relative to their volume. In today's lesson, we delved into the nanoscale dimensions of particles and their unique properties. We began by comparing the sizes of atoms and molecules, which typically range from 0.1 to 0.5 nanometers, to nanostructures like nanoparticles and nanotubes, which range from 1 to 100 nanometers. Next, we explored the crucial concept of the surface area to volume ratio. Using the example of a cube, we understood how reducing the size of a particle increases this ratio dramatically. We then discussed the implications of this high surface area to volume ratio in nanostructures, including their greater reactivity and strength, and understood some of the applications of these unique properties. This insight is crucial for appreciating the advanced behaviors and applications of nanomaterials.